After we've processed the input collection to reduce it to stems and to remove stop words and to enhance the stop list words, we now move on to creating the most important matrix, the document term matrix. In the code here, there are a number of things which are essentially housekeeping. What is the word count, the total number of unique words in the collection? What is the total number of words actually used, the total number of occurrences of words? Then we set, or we have a place here where we can set a number of parameters that will be used later on. I don't want to dwell on them right now because they will be used later on. The first one here is the one that's probably the only one that's important at the moment, and that's the minimum number of words a document vector should have, and we'll see that very soon. We don't want document vectors with only a tiny number of words, because they're really not very indexable. The content quality must have been very low. It may have just been a letter to the editor or something, which is very short. But in any event, we have a minimum number of words in a document vector, and it can be set. It can be set here, and you'll see it used again in a moment. The other ones we'll worry about later on, but they are exported into the environment. So if you see these further down, this is where they are actually set. Now, I now delete the database. I am using my own internal B tree, which is relatively fast, but the easiest way sometimes is just to clean it out and start over again. And the two files associated with the database are key.dat and data.dat. Now, if you're using one of the other back-end systems, you don't have to do this, but the other back-end systems are much slower and you probably don't want to be using them. So this just zeroes out the database, so that means other things will have to be restored. The first thing we restore here is the stems table, because that got obliterated. And that looks like this. Name of the file is loadstems.mumps. Oh, we had a little break there. Something went wrong with the terminal. Control S got hit accidentally. All it does is that you see there's loadstems.mumps. That's the actual execution line. The input is the stems list that was created later. It's a text file. And we read the stems list in, which contains the usual thing. We read in a line. If we run out of text, we exit. We pull off the first item based on a blank. Blank is the separator. The first item is the stem. The second items that and we keep a count, by the way, of the total number of stems. Then we go across the line looking for additional original words. What they are original words that resulted in the stem, and we pull those off. You'll notice it's a piece of I here, so it will be the second, third, fourth piece on the line. And these are each individually. If it's empty, of course, we're done. But each one of those X's individually is instantiated into an element of the stem global array or matrix. And finally, we write out a total count, which is the total number of word stems we're dealing with. It's just interesting. It's not really used for much. And you can see here the output goes into stemCount.txt. And then we print it out. Cat stemCount.txt. Notice it's in the single quotes, which means we evaluate the command, and the result is substituted in here, which is the contents of stemCount.txt, which is just one line with a number in it. The stems.txt, if you I'll do more. What is it? Stemlist.txt. That's what it looks like. And as you can see, there's the stem at the beginning, and then there's the word that generated the stem. Many words, of course, don't, but active, for example, is the stem. Active, actively, activity all got into it. So the first level is active, and we will have the three original terms that generate active above it. All right, so we go back in here, so that just reloads that. Now we come to the document term matrix calculation. I can probably bring this up here as a way of underlining what I'm looking at. That's the comment, but this is the actual execution line right here. The min doc vector words, that's the minimum, that's a parameter to DocTerm matrix.mumps. It tells us the minimum number of words that are allowed to be in a document vector. If a document vector goes below that number, we don't want it. We're going to delete it. You can set this to 0 if you want, which I don't know, a document vector with 0 words would be impossible. But anyway, 3 seems to be a good number. And the input to it is stem.docs.temp. That's our collection. It's been stemmed. Stop list words have been removed. High frequency words have been removed. Low frequency words have been removed. That was our processed input from up above. And the output is going to go into a file called document term matrix.txt, which is just a listing of the document term matrix. Okay, so we will come back to that later. Let's look at it. Document term.matrix. First of all, it kills off these global arrays. df is a vector, dict is a vector, it's the document frequency vector, the dictionary vector, and the global array matrix of this is the document term matrix, up arrow doc, all the way through here, up arrow, these are throughout the entire collection, but up arrow doc is the document term matrix. Now, of course, at this instance, it doesn't exist anyway because a few lines above, we deleted the database. But you could rerun this, and there may be a database, but I wouldn't recommend it. First, we check to see if you passed a parameter. If you don't pass a parameter, we quit, we halt. $1 is the value of the first parameter on the line, and that's going to be, as we set down here, wmin, the minimum number of words permitted for a document vector to be allowed to exist. If it goes below that, we kill it. If well, we would never get here because the halt, but in previous versions I did let it go through and it defaults to 2, but if you didn't provide it, if not $data, in other words, if $1 does not exist, we would have halted. So this line here is superfluous. Initially, we set up a counter, which is the total number of document lines that we will read in. We also open up 2 files for output, dict.temp and doc.temp. And you notice from the comma new that they are being created, therefore they're going to be used for output. We use this for speed up purposes, as you'll see in a few moments. We will write things to these files, then we'll use sort and unique in order to count the number of entries, and we'll read them back in and set up the global arrays. It does work out quicker than every item that you're doing becoming a database transaction. I'll show you in a moment. Anyway, the input here is, the way we process the input's pretty much the same we did in the past. We set to unit number 5, and we do ZZ input, that would be an entire line, into the array W. Now ZZ input operates on the current unit that's open, so we have to turn it to unit number 5 because, as you can see down here, we will be using unit number 2 and unit number 1. So when we come back up to the top, 1 is the current unit, whereas we want ZZ input to come from the standard input, which is how we have routed, if you recall, the document collection. As you can see there, stemdocs.temp is redirected input. If I comes back 0, of course, we're done. There isn't any more input. We extract the offset from the first word in the array. We extract the document number from the second word in the array. We set k equal to I minus 1 because we're going, the W array goes from 0 to 99 if it's got 100 elements. So we want to go 99. It would come back and say it's got 100 elements, but we want the last one we use, of course, to be 99. We increment D, which is a line count. It ought to be the same as doc, but it might not be. Documents could have been eliminated through other procedures that we haven't done, but could have been done. Notice that these are multiple arguments to the original set function command back here. This set. There's one argument, there's another argument, there's another argument, and then there's finally this argument. Up arrow doc, this is the first usage of the document term matrix. And at the high, it's going to be a 3-level matrix or a 3-level tree. At the top level is, of course, the document number, which we just extracted from the input line. That's DOC. And we want to store at this level the offset. That's the offset in the original file where the original document is. So if we need to get to the original document, we can find its address right here. Okay, so at the very top level, it's going to be the offset. And now we go from 2 through K. We're going to process the words on the document. Words 1 and 0 and 1, of course, were the document number, the offset in the document number. And what we do is here we're creating the document term matrix with 3 indices. The first one, of course, is the document number. The second one is the word sub j, w sub j. W is an array. It contains the words of the document. And then at the third level, j. What is j? J is the position in the document of the word. As we read these in, the J is actually the position where the word exists in that large input line. And we set it to empty. Why are we doing this? We want to have a record for later usage of where the words occurred. When we look at similarities between words, we want to look at co-occurrences of words. If 2 words occur close together frequently, that is stronger indication that they are related than if they just co-occur at some random distance from one another. For example, artificial intelligence. If we see that occurring frequently together, we can come to the conclusion that artificial and intelligence are, somewhat related. Plus the fact the order in which they occur. We generally don't say intelligence artificial, but we will say artificial intelligence. So if we get a high signal indicating that the words occur very close together and usually in the same order, that could mean that the words are related in some fashion, either because they're synonyms or because they're a phrase. And so we preserve this information. We've got nothing to store at this point because it just exists. We want to know that in document so-and-so, word such and such occurred at a certain position in the input text. There's no value, so we just store an empty string. Then we write out. We switch to unit number 2, which is doc.temp, and we write out the document number, a space, and the word. Document number, space, and a word, and a new line. And then to unit number 1, we just write out the word. No document number. When we're all done, the last thing we would have done, well, would have been actually, we would have been on unit number 5, but we switched to unit number 5. It's always good to make sure. We close out unit number 1 and we close out unit number 2. The thing, what we've got, well, let's look at what we're doing. Next of all, we're going to invoke a shell. This is unique to my system. I'm sure other systems have a way of doing it as well. What we're doing is passing a command to the operating system to execute. And so the shell command, in my case, the remainder of the line is passed to the operating system for execution. There can be some substitution in here, but there's none in this line, so I won't go further. And what we're doing is we're telling the operating system to run the sort program, take as input dict.temp, pipe the output to unique to count, -c means count, and put the result into dict.sorted.temp. So what would that do? What is dict.temp? Dict.temp is unit number 1. So it's all of these things that gotten written. It's all the words that have been written out. So what is the count going to be? Well, dict.sorted.temp will contain for each word in the collection to contain the number of times it occurred. See, in this line here, when we write it out, that's every time a word occurs, we have written out a line to this output file. This command here will sort them and then count them, because all the ones that are the same are of course going to be next to one another. And we will have in dict.sorted.temp a count and a word. And it tells the number of times that word occurred in the collection as a whole. Okay, so that being done, we're going to create the dictionary vector, which we need later on. We open dict.sorted.temp as old, which means it exists. We're going to be reading from it. This is the output of the shell command, the output of unique, actually. Switch to unit number 1, and we start reading. We read the line in from unit number 1 from dict.sorted.temp. If there's no more lines, we're finished. If we remove all the extraneous blanks, leading blanks and embedded duplicate blanks. Now we create the dictionary vector by removing parts of the line. The word is the second item on the line, and the count is the first item on the line. So the index of dict, D-I-C-T, is the word, and the value stored is the number of times the word occurs. So the up arrow dict vector tells us for each word the total number of times it occurs in the collection as a whole. When we're done with that, we finish that entire loop. We've got the dictionary vector done. We switch to unit number 5 and close off unit number 1. This is a faster way of doing it. The other way of doing it would have been up here. We would have simply incremented. We would have had up arrow dict, and we would have had to increment it each time. It would be something like set up arrow dict sub word equals up arrow dict sub word plus 1. And that turns out to be fairly inefficient. It's better to write them out and just let them and let the system sort them out and count them in one massive operation than to do them in mumps code. This is a quicker way of doing it. But you could see here, every time I had a word, I could have had something like, this is the place to put it. This is where I would be writing out to unit number 1. I could have written something like this. If not $data up arrow dict sub W sub J set up arrow dict sub W sub J equal to 1. In other words, if it doesn't exist, create it and make it give it a value of 1. I left off a make it. So I'm going to delete this. I don't suppose it's really all that important. Otherwise, set up arrow dict sub W sub J close equal to up arrow dict sub W sub J close plus 1. That would have been the operations, and I could have eliminated the output file. Those would have been the operations which would have created the dictionary vector, same result, but you can see it's a lot more accesses to the database. Each of these is technically a database access, even though the files are already, the section of the database is already in memory and it's relatively quick. It's still additional and it's still time consuming. You check to see if it exists. That's an operation. If it doesn't exist, you create it. Otherwise, you will have to reference it, increment it, and store it. So these are the other way of doing it, just writing it out as one massive file and letting sort and unique process it. Sort is very, very quick, and unique is obviously a very simple program, as it goes in, just counts the number of adjacent instances. So anyway, we would delete that. And that's the reason why we're using these output files. Next, we're going to process the actual document term matrix counts. After we finish preparing the dict vector, we move on and we're going to sort, the same as before, doc.temp. Doc.temp, if you recall up here, it's unit number 2, and we wrote it out. What we were writing out was the document number, space, and the word. So for each word instance in a document, we will have a line which says the document number and the word. So if the word aardvark occurs 3 times in a document, say document 100, we'll have 100 space aardvark in the file 3 times. All right, when we get down here, we're going to process that. We take the file of document numbers and words and we sort it, which means for a given word and document pair or document word pair, they will be adjacent in the file. We run it through unique and sort it as we've done before, and the output is doc.sorted.temp. What that's going to be is it's going to be a document, it's going to be a count, a document number, and a word. And what the count is the number of pairs of a particular document and word set that we found. So if the word aardvark was in there in the document 3 times, and therefore there were 3 lines in the file, the line in doc.sorted.temp will be 3, the document number 100, and the word aardvark. So it tells us how many times a word occurred in a document, which is what we need. After we process the shell command, we open doc.sorted.temp old, which means it's being opened for input. We switch to unit number 1, we start reading it. If we run out of it, we quit. We remove the extraneous blanks. Unique adds a bunch of extraneous blanks to it. There's a lot of spacing blanks to make it look pretty, but they're kind of a nuisance. All right, then we will extract the first item off the line based on a blank, and that first item is the count. We extract the second item, which is the document number, and then the third item, which goes into A3, is the word itself, and then we instantiate the two-level values, or the two index levels of doc with the count. So for a particular document number A2 and for a particular word A3, we set the count. Now this already exists, because if you remember, a part of it already exists, I should say. This line up here, this line right here, this is the line where we instantiated the position of a document word combination. It did not that is a three-level thing, and at the third level we stored empty. These intermediate levels exist. As a matter of fact, up arrow doc, sub doc, close paren is actually the offset. But up arrow doc, comma word, in a sense it exists. It's in the path, but it has no value stored at it. This is where we store a value at it when we read it in from in the right place here. No, when we read it in from the file. This is where for a particular document and a particular word we actually store the count. It's quicker this way, again, because the other alternative would be an awful lot of incrementing of individual values, and those are a lot of database operations which are time consuming. It works, and it's not terribly time consuming, but it's better to just write them out, let sort and unique handle it, because they are extremely quick. The other one down here is we create the index matrix value. Now the index matrix is the transpose of the doc matrix, but only the portion of the doc matrix which is the document number and the word, the first two columns. The index matrix does not have the third column. It doesn't have the position. The index matrix is the transpose, which means that documents are document number, and then we have a list of words. In other words, the document number is the row and the words are the columns, and the values for a cell for a given row and a given column is the number of times the word occurs in the document. So for some given document A2 and for some given word A3, the value in that cell in the matrix is the number of times it occurs. But the rows are documents. The alternative to that is the transpose, which is the rows are words and the columns are documents. Same idea, we put the same thing in there, which is the count. So for a given word and a given document, the value stored will be the number of times that word occurred in that document occurred with that word. This is more useful for actual retrieval. So if someone says, give me all the documents for word aardvark, well, I have a nice neat list of them. That vector for aardvark gives me all the documents that it occurred in. We close out and we switch to unit number 5. We close out unit number 1, and now we're going to work on the document frequency. The document frequency vector is the number of documents in which a word occurred. The dict vector, up arrow dict, D-I-C-T, is the number of times the word occurred in the collection as a whole. So aardvark may have occurred 50 times in the collection as a whole, but it may have only occurred in 25 documents. The document frequency never exceeds the word frequency, because obviously if you had a word that occurred only once in every document, then the two values would be the same. But generally speaking, at least we hope that words will occur more than once in a document. So we open up a df.temp. You can see where we're going here. It's going to be similar to the previous usages. We switch to unit number 1. We start going through the document matrix by document number. And so the D's will be they'll be going through all of the document numbers. They're not going to come out in numeric order, because, at least in mine, because everything's stored in alphabetical order. They'll come out in the alphabetical ordering of numbers. But anyway, the D's will be the document numbers. All right. First of all, we want to count the number of words in the document vector. because this is the time to start pruning document vectors if they don't have enough. So we set C equal to 0, and then we go through all of the words. This situation. This is, by the way, something different than mine. This is a form of the for loop, which I don't believe exists in other versions of MUMPS, but it essentially iterates as long as W is returned. As long as it's not blank, it reiterates on the a running order, and we get successive values, and those are the values used in the loop. So it gets all of the values of W and increments C for each one of them. So at the end, C is the total number of words in the document vector, usually a small number. But if C is less than W min, which was up at the top of the program, as you remember, if it's less than that, we want to get rid of it. Well, first of all, we go through all of we have to individually kill it. Well, we could kill it, I think. There's another way of doing this, but this is the way it was done. We want to kill it by word. We go through each of the individual words. Here again is this odd usage of the for, special form of it. We get the individual words, and we kill the individual elements, or individual rows, actually. No, the individual elements of up arrow index. So if word W exists, and D, of course, will exist in it, we destroy it. So it's removed, first of all, from the index array, and then we delete the entire row from the doc array. That deletes not only up arrow doc sub D, but also of its descendants, all of the comma W's. So they all disappear, also the third level in it, where the positions are. Otherwise, this assumes that the thing actually, the word actually, that the word count is greater than W min, or equal to greater than W min. We go through it, and we write out for each word the word. So what we're doing here, so in other words, the vector has enough words in it, and now we are going to go through the vector, and we're going to write out each of the words to the output file. What that is telling us is that if the word aardvark exists in the document, there'll be only one instance of it here in the up arrow doc D comma W. It'd be there once. The value stored here will be, let us say, 3, but it'll only be here once. So if I write it out, that indicates there was one instance of this word in a document. So if the word aardvark exists in 10 documents, and regardless of how many times it exists, there will be 10 instances that look like this, 10 instances of up arrow doc sum D for aardvark. So we will write aardvark out 10 times. The number of times aardvark appears in this output file is going to indicate the number of documents in which it occurred. When we're done with this, we close it off, and we run it through the sort, as we've done before. The file dftemp, we sort them by words, we count them, and we write it to dfsorted.temp. So we get a lot of intermediate files here. Then we quickly open them again as unit number 1. Now it's old, it's for input, and we start going through it. Going through that file, we read a line in. If we're out of data, out of lines, we quit. We remove the blanks, and we first of all grab the word, which is the second item. The word is the second item on the line, and that will become the index of the vector df. Document frequency is what it stands for. So it'll be df sub the item, the index will be a word, and the value will be, I say, plus a. Well, a is the line. Well, the line consists of a number, blank, and then words. Well, if you use a numeric operator with a string, it converts the string into, if possible, into a number. If not possible, it converts it into a 0. So the numeric portion of the line is the first part. So the value of plus a will be the value of the numeric portion. For example, if a string has the value 123 space Elm Street in it, and you put a plus sign or any other numeric operator in front of it, all you get is the 123. The remaining non-numeric portions are lost. So I use that fact here rather than running the piece function. I just run it through the mathematical processor. It's a little bit quicker. So when we're finished with this, we're going to have a vector called df. And the individual elements of df are going to be, it's going to be indexed by words, and the value stored will be the number of documents a word occurred in. Okay, now I close this off. I switch back to unit number 5, and now I'm going to now I'm going to go through and get another count, to get a count of the total number of documents, because in this process above I may have lost documents. Probably did, documents that didn't have enough words. So I go through all the documents, and for each document I increment C, and when I'm finally done I create a global array element called global array vector, which only consists of one element, which is the count. So up arrow doc count, notice the caps, is available in the database. It tells me the total number of documents that are currently in existence. There probably were more, but they got some got eliminated. We also write that out to a file. The file is called docCount. We write out one line to it, and that is the number of documents we have left, and we close that off. Finally, down here, we are just going to we're going to print out the document term matrix. For each document, we write out the word doc and a space, and then the document itself. And then we set I is equal to 0, and then we go through all of the words on the document, writing out the word, and then parentheses, notice it's in quotes, and then the count, and then a closed parentheses. So what we're getting is a word, space, parenthesis, the count of the number of times the word is there, closed parenthesis, and we increment I. We increment I because this is our formatting thing here. If I modulo 10 is equal to 7, I write out a new line. Notice that's a post-conditional. So I will cycle every 7 words, every 7 of these things here. Every 7th time I will write out a new line. So it just keeps the lines from getting extremely long. Finally, when I'm all done and I've written out all of the words and their associated counts, I write out 2 new lines to separate this document from the next document. Finally, down here, I'm going to play around with the word frequencies. Finally, we display the vectors that we built up. We open up a file called termfrequencies unsorted.temp, and we go through the words one by one using the df vector. It doesn't matter which one because they all have the same words in them, presumably. We get the words and we write out the value of the document frequency for the word, a space, the value of the dictionary vector, the term frequency vector, and the word itself with a new line character. So we just simply write out document frequency, term frequency, and words. And then we close them off, and then we run it through another sort. This time, notice it says NR, which means it's going to be a numeric sort, and it's going to be in reverse order. The first thing on each line is the document frequency. So we were sorting them by document frequency. Again, the N means it's numeric sort, not an alphabetic sort. And the R means reversed order. Instead of the lowest first and the highest last, it'll be highest first, lowest last. So and the output of that simply goes into the resulting file, termfrequencies.txt, and then we halt. Now we have built up the major matrices that we're going to use. We've built up arrow doc, which is the document term matrix, which also contains position information. We've got the dictionary vector, which tells us the total number of times each word occurs. We have the document frequency vector, which tells us the number of documents in which each word occurs in. And we also have the index matrix, which is the transpose of the document term matrix, which gives us by row the words and by column the documents. It's just turn it on its side, basically. So now we need to run it. All right, now we're going to run the file. I inserted an exit in index.script right after the document term matrix, so it'll only go that far. So it's index.script, and we'll give it 1,000 documents, which is a bit on the small side, actually. Normally, I'd prefer to go something much larger. So we're seeing all the numbers float through, and now the document term matrix is is finished. We've got some statistics that came out. These were the values that were set up for parameters that are not being used right yet. And at the end, it turns out document count after deletion of documents with fewer than 3 words, we're down to 906 documents. So there were several documents which had fewer than 3 words. All right, let's look at the results. First of all, we want to look at the document term matrix. Term matrix here. This will be the resulting document term matrix. Now notice the documents are coming out in alphabetic order, which is normal. And we see the first document, it's got the word absence, which occurred 5 times, absent 1, acetaldehyde 5, action, alpha, alteration, amino, and so forth and so on. And then the second document, which contains 4 words, and it's letter of the editor or something like that. And so forth. We see some of them are relatively short, most of them are roughly the same size, but there's a few that are outliers. But these are this is the document term matrix by document. For each document, I'm giving the row, and you can see the words, you can see the count. This is our document term matrix. The index matrix is flipped on its side, and it would be by word. We don't see the positions. So, for example, the word amyloid here occurs twice, and where does it occur? Well, it's stored, but we didn't print it out here because you'd have to print it out twice. The other output file is termfrequencies.txt, and that looks like this. And it's ordered by, if you remember the columns, it's the document frequency is in the first column. That's the number of documents a term occurs in. The overall term frequency is the second column, the total number of times the term occurs in the collection as a whole. And finally, there is the word itself. So we find the word demonstrate occurs in 80 documents 95 times. The word include, correlate, these of course are the high numbered ones here are going to be relatively less useful terms, but they're still in there. We could of course increase the stop list thresholds as well. But this is what they look like. As we're coming out, we get down to the middle range, like the word hormone occurs in 27 documents 48 times. The word uptake occurs 27 documents 73 times. As we go down the list here, chemotherapy occurs in 12 documents 30 times, that sort of thing. So the relationship to the number of documents a term occurs in versus the total number of times it occurs gives us an idea of the concentration of the term. If a term is heavily concentrated in its usage, it's probably important, is the general theory. All right, so that's the document term matrix. There was, before we did that, there was actually a tiny error which was discovered. Let me go in here and show it to you. Document term matrix in this area right here when I was writing out, no, it's not there, where I did the document frequency output here. When I ran out the output file, yeah, this is the area right here. Some of these indent levels were incorrect. And this is the correct order. So we have a loop based on the documents, and then we counted the number of words in each document. If the number of words was too few, we basically deleted the document and its corresponding rows in corresponding elements in the rows of index. Then killed off the whole document. Otherwise, we wrote it out, and there was someplace along the line, one of the dots got deleted, and that caused a problem. So you may want to check it. It'll be in the updated online files.